Okay, let's start our next video. Oh man. Oh, it's always a pain to get this thing in here. Okay, so 3.2. There's an interesting theorem. Now, the theorem lurks in the background. In other words, it's not the theorem itself that is really you're constantly focused on. It's what the theorem ends up doing. And then it ends up doing something that you always end up doing, but then forget that the theorem caused it. And so that's what this next theorem's like. It only lives in the background of a lot of things, but it doesn't live on the surface. But it lives in the background, but at the same time it causes those things that do live on the surface. And the theorem's called the mean value theorem. It's 3.2. Mean value theorem. It lurks in the background of a lot of things that are meaningful, but it itself on the surface doesn't seem too meaningful. It's what it causes. And then after it causes those things, you forget about the theorem that caused them altogether. And this is what happens to the mean value theorem. But anyway, let's state it. So it goes like this. Mean value theorem. Okay? Let f of x be a real nice function, be continuous. Be continuous on, let's put some lines here, on a closed interval, say a comma b. So it's a really nice function, continuous, and differentiable on the open interval. What does differentiable mean? Remember from 1.8? It means you have a derivative on this open interval, AB. Okay? In other words, the derivative exists there. So if you feed in the derivative a number from this interval, you always get a number out. Okay? Then what the mean value theorem claims is then there exists another number. Exists a number C inside the open interval AB so that this happens. So that the derivative of our function at C is equal to this interesting quotient, f of b minus f of a over b minus a. And that's the mean value theorem. Let's have a look at why it's true, because why it's true is quite childish. So why is this true? Why is there such a C that makes this equation work? Well, imagine your function. Maybe it looks like this. Here's AB. Here's the interval AB. Okay? Suppose the function went like this. Over this interval, look like this. Your function here, f of x. Suppose its graph looked like that. Then if you look at this point, the coordinates are a over and f of a up. So its coordinates are a, comma, f of a. And if you look at this point up here, well, to get to it, you went b over and f of b up. So its coordinates are b, f of b. What you can do then is connect these 2 points with a straight line. Okay? And now I'm going to find the slope of that line, because from high school I know the slope of a line through 2 points is the rise over the run. Okay, so I'm going to calculate the slope of this line here. You ready? the slope of this line would equal, well, the difference in the rise, that will be f of b minus f of a. That's how much you rose between the 2 points, the difference in their y-coordinates, minus how much you ran to get from one point under the other one, b minus a. So there is the slope of that line. Does that look familiar? Well, it's the number in the box here. See it? Okay? Now you can see that I could draw a tangent line that's sloped exactly like this line somewhere. In other words, it looks like right here. These two lines have the same slope. Another place is here. See that? Looks like all three of these lines have the same slope. So if I call this point C down here, there'll be some real number that's underneath it. Then the slope of this line, well, it's a tangent line, so its slope is equal to the derivative of the function at C. But at the same time, its slope is the same as the slope of this line. You can see they're tilted exactly the same, which is this number in the circle. So I get f prime of C is equal to f of b minus f of a over b minus a. Okay? And you can see it even happens at other points too, like over here. There's another point where it happens. All the mean value theorem insists is that there's at least one C that makes it happen. And there could be more than one, like in the picture I just drew right here. Looks like there's two. Point right here does it too. Because again, the line is tilted the same way as this line connecting AF of A to BF of B. Okay, so that's why it's true. Now let's have you verify it a couple times. So you should be aware of what the mean value theorem is because it causes certain things. I think it will cause at least one thing in our class, but it causes multiple things in Calc 2 to happen. And that's why it's true. Okay, so for example, just to see if you understand the statement and remember the statement, you could be asked questions like this. Find the numbers, find all the numbers C. Find all the numbers. All of them. Could be more than one, like we saw from the picture, that satisfy the conclusion of the mean value theorem. For this function, f of x is x cubed minus x on this interval, the closed interval 0 to 2. Okay, so first notice that this function really is continuous on this interval because it's a polynomial. Polynomials are continuous on the whole real line. And second of all, notice that the derivative always exists on this interval. The derivative is 3x squared minus 1, and you can feed any number between 0 and 2 into it, and a number comes flying out every time. And so we really do have a continuous function on a closed interval, and it's differentiable on the interval as well. So there are C's that satisfy the conclusion of the mean value theorem. So realize who's who. A is going to be 0, B is going to be 2, and we just now set up an equation. Our derivative, f prime of x, is 3x squared minus 1. So you have to realize all of these things, a whole 3 things. Okay, and now you set up the equation. Remember the conclusion. There's some c where f prime of c is f of b minus f of a over b minus a. Now I'm just going to fill in all this. F prime of c, well, here's f prime. It'd be 3c squared minus 1, and that would equal f of 2 minus f of 0 over 2 minus 0. Work it out. We know what f is. It's up here. Stick 2 in, stick 0 in. Subtract. So you could say 3c squared minus 1 is equal to f of 2 would be 2 cubed is 8 minus 2 is 6. Minus an f of 0 you can see right here is 0 over 2 minus 0. Okay, so I just plugged it into that f. And then you can say 3c squared is really, this is all just 3 over here. Add the 1 to both sides. You get 3c squared is 4. Or divide both sides by 3. C squared is 4 over 3. Take the squares of both sides. So we get two possible c's, plus or minus 2 over root 3. Okay? But now be careful. We're looking for the c that satisfies the conclusion of the theorem. And for that c, I'll remind you, it says right here, it's in the interval. Yeah, it's the c that's in the interval. Okay? The c in between a and b, like right there. In between the a and b in the interval. So going back to our work, if you look, one of these points is not in our interval. Look at our interval. It's 0, 2. Look at our points. One of them is not in the interval. Okay? So you can say, but negative 2 over root 3 is not in the interval 0, 2. So the only c that satisfies the conclusion of the theorem is the one that is. 2 over root 3 is between 0 and 2. So we only get one c that satisfies the conclusion of the mean value theorem is c equals 2 over root 3, the positive one, because it's the only one in the interval. Okay? So with that being said, these are problems simply asking you to do what I just did on different functions. Okay? So so the homework is just doing that. Okay, so 3.2, it is just doing that a few times. How about 11 to 14 all? Okay, so find all those c's in those intervals that satisfy the conclusion of the mean value theorem. You can see why the mean value theorem is true. You saw the pictures. There really are places where the tangent line has the same slope as the line connecting a f of a to b f of b. Okay, with that being said, I'll see you in the next video.